All right, so last class we did addition of water across an alkene. Now we basically are going to start we are going to add hydrogen to make alkanes. We are going to add what we would call carbenes to make cyclopropanes. We are going to add we're going to have a source of basically oxygen, and it's going to make a epoxide. So this is a three-membered ring with it, which has got a oxygen in it. Cyclopropanes are a three-membered ring with carbon in it. So both of these are quite similar reactions. Then we are going to add OH across two carbons to make what we would call diols. And what else are we going to do? Right, then there's some reactions that we can do that will cut this bond in half and make carbonyl compounds. So ketones, aldehydes, and even carboxylic acid. So this is going to be a cleavage reaction. So we call this oxidative cleavage. So yeah, so this is basically what we need to do next. Which one shall we do first? Let's do hydrogenations. I think that would be the best. So this is the addition of H2. So it's the addition of molecular hydrogen. And so on this pun here, on the surface, this reaction doesn't seem that interesting because what we would have is, for example, H2, and we need some sort of catalyst. And there's typically a solvent of some kind, solvent. And we are adding hydrogen across this double bond. So each carbon gets a hydrogen, and it doesn't, and this would give an alkene. Sorry, an alkane. And this doesn't seem particularly interesting. Now the typical catalysts are transition metals. So the ones that have become the most popular are catalyst. Things like palladium, platinum, iron, nickel. The ones which have gotten the most sort of use in chemistry labs tend to be these two, but the advantage of these ones are that these are expensive. And these are less expensive, but the reactivity sometimes requires heat or something like that. So there's quite a bit of research going on around nickel and iron catalysts to allow these to take place at lower temperatures and that sort of stuff, so it'd be more effective. So the one that we'll see the most is palladium on carbon. So this is when you're in the lab and you might have used, well, actually this year we didn't probably, you might have used it, no. Activated carbon is sort of this black sooty looking stuff. Well, palladium on carbon, palladium is basically infused on the surface of that carbon. And so for this reaction to take place, you need the surface of the metal is really important. So the way it works, and this is, here's a hypothesis of how this works. Okay, so you've got your metal surface and you've got hydrogen, and then the hydrogen gets basically absorbed onto the surface of the metal. So you're breaking the hydrogen-hydrogen bond and you're, so this is the surface. To make, so the hydrogen's now attached to the surface of the metal. And then you've got your double bond. Your double bond's going to come along. I'll draw it like this. And so it basically goes that the p orbitals of the pi bond, the p orbitals of the alkene sort of interact with the surface of the metal, and they and something like this takes place. Probably the easiest way to draw this, although it's not exactly 100% correct, is that if you are the, because the alkene itself is supposed to interact with the surface of the metal. So you sort of form a, I don't want to draw a formal bond here, but this is sort of forming an interaction with the surface of the metal. And then the hydrogen comes in and basically forms a bond there. And then this is forming a formal bond there. Like these arrows aren't correct. There's lots of, this is just a way of showing it. So you would have your carbon then would have a bond, proton here. You'd have another H. And then you're going to end up breaking this bond here with the metal. So these electrons would go back onto the surface of the metal. And in the end, the key point for the, like a lot of the evidence that suggests that this is what's taking place is that the two protons, or the two hydrogen atoms, I guess would be a better way of saying it, these two guys are on the same side. So if you've got a, so if you've got like a molecule like this, let's draw it like this. And you were to do a reaction with, say, H2, palladium on carbon, and some solvent like ethanol, then your product should be and these guys are on the same side. So the two hydrogens are on the same side. So if got a tetrasubstituted double bond, and we've got no free rotation here. These two H's should be on the same side. Now, at this stage here, right here in this mechanism, if this is truly the way it works, then there should be a brief amount of time where this bond could rotate and the hydrogens could be on opposite sides. But if you've got a fixed, like a cyclic system where there's no possibility of rotation, then you would have both hydrogens on the same side. Now, there's some sort of added evidence to support this, in that if you are the surface of a metal, so this is the metal surface, and you're the alkene, so the reactive part of the molecule, the alkene, this is trigonal planar, right? Because those two carbons are sp2 hybridized. But if you, let's pretend that we are this molecule here, and you have got something sticking out, like something which is big and bulky on one side of the molecule. So this compound here is called alpha pinene. And when you do the hydrogenation on this, the side which has got all of the sterics would be the bulky side would be up, and to allow, so if this was to approach the metal, this large group would be not on the side of the metal, but on the side opposite to the metal. So that would mean that the hydrogen is added on the opposite side. So if we did this reaction with H2 palladium on carbon, we would expect that the main product here would be that this methyl group would be up, and it would be on the same side as this large bulky group, because it would have to approach the metal on the opposite side. So what's the best way to draw this? So the bulky side would be over here, and the surface of the metal would be here. So if the protons are added, they'd be added from the opposite side, which would mean the methyl group over here would end up being up as well. So yeah, that's basically, this isn't, it's not a hydride per se, but the way I've drawn it. But and I haven't drawn the proton over on this carbon because that carbon's got two protons on it. So it's irrelevant to if it's up or down. So this would be the main product. This would be the sole product. And not this. Because that would mean that the hydrogen is up, not formed. Now, there's one other little bit we could include here. If we wanted to, like, let's pretend that we've got this as our molecule. And we do this reaction. H2 Palladium on carbon, ethanol. The product is this, right? I could draw this H down. Like there's no point in drawing, like particularly on this carbon right here. There's no point in drawing that H down because this carbon here has got 2 protons on it. So it makes that kind of question kind of useless to ask on a test. So rather than doing it like drawing it like this, the question I would ask, because the key point here is that there's 2 key points. One, H is added on same side. That's one point. Second point is H is added on less bulky side. So it's added on the same side. This means it's a syn addition, and it's going to be added on the less bulky side of the thing. So in a case like here, where there is no bulky side, if I was asking this question on a assignment or on a test, what I would probably want to make sure that everyone understood is that the H's are added on the same side. They're added syn to one another. So what I would probably do is instead of using hydrogen, I would use the isotope deuterium to do this reaction. And that way, I would have to draw those 2 protons, deuterium atoms on the same side. So I would draw something like, depends how we do the zigzag here. Let's draw it like this. Or I could draw it like this. Oh, that's bad. That's not what I want. Something like that. So the 2 deuteriums are on this, are cis to each other. Now, practically, this deuterium, this would be not something that you would, deuterium gas, that isn't something you would find very often, but it's just something to do theoretically to show that the 2 deuteriums are added on the same side of the molecule. Now, what else is next for that? So if we had, let's pretend that we have this as our So we've got A, B, and C. The answer, the best answer for this question is which one? C? Right. So that's correct. C would be the best answer for this. Okay, what's wrong with A? Right. So the problem with A is that the problem with this one is that D's are on the more bulky side. Okay, what is the problem with B? Okay, so yeah, we want the problem here is that the D's should spell that right. They should be on the same side. So they should be it should be a sin addition, sorry. I think I drew cis before. Yeah, it should be sin. So they're not anti to one another, they're on the same side. And so when it's squiggly lines, this means up and down, up and down. So we would have a grand total of 4 different diastereomers would be possible here, right? Yeah, so this is that's the problem with B. Okay, good. I think that's good. Were there any questions on that? Right. Okay, so let's do another example here. Let's do a couple more. Okay, let's pretend that we've got let me think here. What's a nice example which would be okay. Let's do this. Okay, this is a relatively and let's pretend that we've got this as our Okay, so something without free rotation, and it's got an isopropyl group. Okay, so H2 palladium on carbon ethanol. Oh, I guess I should bring so this for these reactions here with double bonds. You might say to yourself, well, how do you actually do this reaction? It's relatively straight. It's relatively straightforward. It's kind of fun actually. You have a little flask, round bottom flask that would have had in the lab. Here's your stir bar. Throw in your catalyst, palladium on carbon. So it's a solid catalyst. You've got your solvent, and you throw in dissolve your product in there. So get your product, or your starting material, sorry, dissolved in that. You basically you stopper your flask with a septum, so something which is which you can puncture with a needle, and then you just have a little needle going through the septum, which is attached to a balloon which has got hydrogen in it, and you can stir it, and then the hydrogen is going to gradually get dissolved or into the solvent, and then it's going to reach into it's going to absorb on the surface of the metal, and then the reaction is going to take place. So it's basically you've got a little septum with a party balloon in it, and it gradually gets into the water. So for all of these reactions, there's no pressure or anything needed. We're going to see in a second that if you want to reduce other functional groups with hydrogen, sometimes what you'll need is a pressure to the system, and that makes things slightly more complicated. But for what we're doing here, it's a really simple reaction to actually do. And then when the reaction's over, you can basically filter out the catalyst because it's on that solid, and then you've got your liquid with your product in it. You can just evaporate the liquid, then boom, you've got your product. So it's relatively straightforward. So in this case here, with this example, we're using hydrogen. So we don't need to worry about this carbon here has got no other alkyl group. It's just got a carbon with a proton on it, or hydrogen on it. So for this, what we've got, our product is going to be the question, which is the important question here, is one side of the molecule has got some sort of steric hindrance on it, and the other side doesn't. So when hydrogen's being added, it's going to add on the opposite side to the isopropyl group. So our product should be this. So both the isopropyl and the methyl are now up because this H is down. If we did the same reaction with D2 palladium on carbon and ethanol, then in this case, there's two things we need to worry about. The first thing is that we want the methyl group to be up and on the same side as the isopropyl group. And then the second part is that we need to actually show, okay, this deuterium's down, this deuterium's down. So it depends on what the reagent is for what you need to worry about. So if it isn't deuterium, you just need to show that the methyl group would be on the same side as the isopropyl group. Okay, now, the fun thing about this is that catalytic so the palladium on carbon is just a catalyst, right? It's the place where the reaction takes place, but it's not consumed in the reaction and it speeds up the reaction. So that is basically the palladium on carbon is the catalyst. So the neat thing is the catalytic hydrogenation is, I'll say generally, chemoselective. So chemoselective, what in the world does chemoselective mean? This is when one functional group reacts preferentially over another. So, and that's kind of neat. So one functional group will react, another one won't. So some examples would be if you've got a ketone and it's conjugated with a double bond. So this would be an enone. Ene for double bond, one for ketone. When you do this reaction at room temperature and standard pressure, palladium and carbon, the ketone itself, you can stop the reaction before the ketone itself gets reduced. So you end up with basically just a ketone. Now, it is possible to reduce ketones with hydrogen, and there's certain catalysts that have been designed to do that. But with palladium on carbon, this is you can easily stop the reaction before the ketone starts to get reduced. Some other examples would be this. So how would you stop the reaction before the ketone gets reduced? Okay, so there's ways of whenever you do a reaction, what you would want to do is, okay, there's some reactions that need to be what I would call you know, when you go babysit somebody, you're looking out for the kids so they don't, I don't know, jump off the stairs, break their legs, drink something toxic or whatever. So you're basically there to make sure that they don't hurt themselves in a so the same sort of thing can apply to a reaction. So the you can monitor the reaction so that there's a possibility here. You've got two functional groups. You've got the carbonyl and the double bond. So there is one, if this reaction was to keep on going, you could conceivably have this as a final product. Now because you can reduce ketones with H hydrogen. But the trouble is that this catalyst isn't designed to activate the carbonyl to reduce it. So that's the first thing. So in the lab later on, you're actually going to do a reaction which is the reduction of benzophenone with sodium borohydride. And what you're going to do is you're going to monitor that reaction with a TLC plate. And it's the same sort of thing here. You can monitor the reaction to see that this has been reduced. And when it's reduced, you basically just stop the reaction. So that would be babysitting the reaction. Other reactions where you just leave them overnight and you don't worry about it, those are things that if you didn't care, then it could go all the way to here. So it's just a way of monitoring the reaction through TLC would be one of the things. Thin layer chromatography, TLC. The enone has got a specific, on a TLC plate, you can visualize it in a certain way and it's obvious that it's that. The ketone would have it be visualized in a slightly different fashion. And so you can just wait, oh, that's all gone and that's been formed. So anyway, but palladium on carbon isn't particularly efficient at reducing carbonyls. Other catalysts would do this far better. So that's one of the things. Some other examples. Now here, we've got two other functional groups. One, the aromatic ring, and the ester. So it turns out that if you want to reduce an aromatic ring, you need high temp and high pressure if you're using hydrogen. So this is basically immune, and an ester is even less reactive than a ketone. So you can selectively reduce this double bond and make your ester. So yeah. And I guess the other example, there's another example I have in my notes about a nitrile not being reduced as well. So it is possible to reduce nitriles, but there are more efficient ways to do it than palladium and hydrogen, and you can actually do this without reducing your nitrile. So with monitoring and stuff, you can chemoselectively reduce the double bonds in the presence of other carbonyl groups, aromatic groups, and even nitriles. So it's a nice little reaction. So, and it's really easy to manipulate. As I said before, you just have a balloon with put some hydrogen gas in it and puncture it through your septum and let it stir overnight, and you come back the next day and you would have produced your product. So that's good. Okay, I guess the next thing we should talk about is carbenes. So this is the way of making cyclopropanes. So you've got your, stop it. I'm going to put this in quotes for a second. And I'm going to put a little positive here and a negative. And the product that we make is this. And the three-membered ring is a propane, and because it's in a cycle, we call this a cyclopropane. And let's say that the other thing, which is interesting is that if we have got so what type of alkene is this when we're talking E or Z? Is it E or is it Z? Do we remember which one is which? Z. So right, Z is the if you do a priority R1 R. So with the Z, the highest priorities will both be on the same side. So we've got the higher priority ethyl group, ethyl on the same side. And you will notice that in your product, the two ethyl groups are on the same side. So if you start with a Z alkene, you are going to have a propane, cyclopropane, with the two highest priority you'd have on the same side. So it's going to, and if you start with the E, they will be on opposite sides in your product. So that's the key thing to worry about. But so this is what we would call a stereospecific reaction. The stereochemistry of your starting material is reflected in your product. So this would be stereospecific. If we don't have a definition of stereospecific, I'll dig up a better definition of it. But basically, it's saying if you start with Z, you're going to end with it's going to be Z, and if you were to start with E, you would end with E. So the stereochemistry of your starting material is important for your product. So in an SN2 reaction, this is stereospecific as well. You get inversion of stereochemistry. So if you started with S, or that stereocenter is going to be inverted. So anyway, this is sort of a key. So so the mechanism for this suggests that all of the bonds are being broken and made at the same time. So it would be a concerted type of reaction here. Now, what does a carbene look like? So it is an interesting molecule. So if we've got a carbene which has got a positive and a negative, like the way I've drawn that, CH2, it would look like this. So you've got an empty p orbital, and you've got a orbital with basically a lone pair. Now, if you take some inorganic chemistry classes with Dr. Yan, there is basically another type of carbene, which if we were to draw it, you would put one electron in each orbital. And so, and in fact, are they hybrid orbitals, or are they, because this one's got a p orbital and a hybrid orbital, or is it just tetrahedral? So there's really two types of carbenes this type is basically, most textbooks only in organic chemistry discuss it like this. So this is something you'll discover in inorganic. So we'll focus on the one on the left. So if we think about our double bond, so if we've got our double bond here, and we've got our carbene, the way that this would work is that your double bond is still the nucleophile. So these electrons go up to this orbital. And then as that's going on, the lone pair would come down to the other orbital. So this would basically be sort of a concerted reaction. And our final product would look like this. And of course, we would normally not draw these two protons here because they're just protons. But that's basically the way it would work. So so the generation of carbenes is an interesting question. So a lot of carbenes, Fischer carbenes, for example, they're made through transition metals. So I've drawn this as, this is why we sort of put quotation marks around this, because it's not really floating around in such a fashion like that. It's usually connected to a metal of some type. So if you want to have like two hydrogens associated with it, the way that we make this, the most common way is what we call a Simmons-Smith. Simmons. And you basically start with diiodomethane and you react it with zinc, and you react the zinc with what is that reagent we react the zinc with? Copper, right? I did this. I can't even, and it's done in ether. And what happens is that you basically insert the zinc between one of the carbon iodine bonds, and this is effectively CH2 plus minus. So you could think that, so if we're thinking of this, let's draw this out here. If you think of this as a, so the carbon iodine bond, you think this is delta minus, this is delta plus. So you've got carbon with a positive charge. And if you think of the zinc carbon, zinc is more electropositive. So this would be, you know, carbon delta minus, zinc delta plus. And so carbon's got both of these plus and minus. So if you ever see diiodomethane, zinc, and copper with ether, you're basically making a carbene. So this is the first step of making the Simmons-Smith carbene. Another way of doing it is, in this case, there's not protons here, it's chlorine atoms. So you take chloroform, and you react it with potassium hydroxide. So chloroform, of course, this is a solvent. So you could do this reaction in chloroform. And what happens is, let's erase this for a second. Plus, minus. So I'll do the proposed mechanism of how this works. So we are going to remove this proton. So this proton here on the chloroform, there's these 3 chlorines which are all electronegative. So that makes this proton like acidic enough that it can be removed with a base. This generates carbon with a negative charge. And this causes one of the chlorines to leave. Disproportionates, I guess we would say it. And you make carbon minus carbon plus Cl. So it's made in situ, and then this reacts with whatever your alkene would be. Let's use this as our example again. But the only difference is that here, the thing you need to worry about is that, so this comes in and attacks positive. This comes down there. Is that with this carbene, the cyclopropane has got two chlorine atoms attached to it. But if you start, same sort of principle applies. If this is a Z alkene, the 2 ethyl groups would still be on the same side. The 2 methyl groups are still on the same methyl, like methyl, they're still on the same side together. The only difference is that you've got some chlorine atoms here. Oh, yes. If I haven't done that already, yes, I will be providing practice questions. They're on Moodle. I just haven't revealed them. I'll do that today. I'll do that right after class, actually. So if we go back to here, we basically we got through this part and this part today. So I guess on Thursday, we're gonna have to do making the epoxides and the diol. And this oxidative cleavage, these two are related, so it makes sense to do it in this way. And then the last thing we'll do is the oxidative cleavage. This reaction is kind of interesting. To make ketones, aldehydes, and carboxylic acids. So we'll do that on Thursday. And I think that's basically it for alkenes. Then we'll do the alkynes, and that is very similar to this. It's just history repeating itself, except for we've got 2 pi bonds to break or react, whereas in this case, we've only got 1. So a lot of the stuff is exactly the same. So I guess that's basically it for today. So mechanistically, for most of these things, I typically don't ask mechanism questions on carbenes or necessarily on hydrogenations, because there is some debate in the literature of just how the hydrogenation works. But the observable sort of consequences of these reactions are that the hydrogens are added on the same side, and it's usually the least bulky side. And with regard to the cyclopropanes, the key points is that it's a stereospecific reaction. So if your double bond is E, you've got to maintain where those groups are in your product, because you can't rotate through a cyclopropane because it's a fixed rigid system. So the group should still be E in your final product. So those are the takeaway things from both of these sort of mechanisms or reactions. We'll see that the epoxidation reaction is very similar to the cyclopropane. So remind me to start there on Thursday, because it's a good starting off point. All right, were there any other questions for today? And I'll reveal some of the practice questions on Moodle right afterwards. Okay, well, if not, I hope everyone has a wonderful day, and I'll post the lecture video on Top Hat once everything's done.
Thank you.
You bet. Yes, hope everyone has a super good day. This